Okay, Nalin, here's another problem. Consider a vertical square duct with incompressible fluid flowing in the downward direction. Use the shell balance approach and describe in detail how to deduce the differential equation. Also give the correct boundary conditions. Explain with reason whether it is possible to have the velocity profile for a flow as given in the equation below.
Okay, so see, in this case, your velocity would be a function of two directions, that is both x and y, considering z to be this direction, y and x, and after that vz would be 0, and after that, basically vz would be a function of both x and y, vx and vy are 0, like what I was saying.
Okay.
And then you can use basic shell balance, and after that, when you substitute the Newton's law of viscosity, there you might get terms like dou square v by dou x square and dou square v by dou y square, like in an equation. And then a velocity profile equation is given. So you can partially derivate it two times, first with respect to x to get dou square v by dou x square term, and then with respect to y separately two times to get dou square v by dou y square term. And then you can substitute those dou square v by dou x square and dou square v by dou y square in that equation which you got after substituting Newton's law of viscosity, and then you can equate it and check like what the result is coming.
Okay.
From that you can explain whether this velocity profile is correct or not.
Okay, we have to check whether it will come or not. Right.
So first we will draw the diagram. We will choose Cartesian coordinate system for this problem. We will specify our directions like this. This direction will be our y, this is z, this is x. We will choose origin at this point. All the lengths would be 2b since this is a square duct. Now in the question it was given that the fluid is incompressible and the flow direction is downward, so therefore only Vz would be non-zero and Vx, Vy will be 0. But Vz will be a function of x and y. Vz is not a function of z. Pressure will be a function of z direction due to gravity. We specify the dimensions, they will be in x, it would be from minus b to plus b, in y it would be minus b to plus b again, and in z it would be 0 to 2. Now we will take differential elements. Delta x and delta y. Now we will apply shell momentum balance. Shell momentum balance is basically the rate of momentum in minus rate of momentum plus external force, which here is gravity, and because it is steady state, so accumulation is 0, therefore on the right side we have 0. So now we will write flux. Equation for flux phi ij is basically T rho ij plus rho vi vj plus T tau ij. So phi xz will be 0 plus 0 tau xz, which is minus 1 dou vz by dou x. 5yz will be 0 plus 0 plus tau yz, which will be minus mu dou vz by dou y. And 5zz would be 0. Sorry, we will have p here because dou ij is 1 when I is equals to g, and dou ij is 0 when I is not equal to g. So it will become p plus rho vz plus rho vz into vz plus 0, because velocity is not a function of z direction. So now we will use the shell balance equation. So 5xz x, we will multiply with the cross sectional area perpendicular to that flux, minus 5xz x plus delta x L into delta y plus 5yz L into delta x minus 5yz y plus delta y plus 5zz L delta x. It will be delta x delta y. 5zz x delta x delta y. 5zz and z plus delta z. We have an external force of gravity, so that would be rho delta x delta y L. This is basically the volume of differential shell, and volume multiplied by density is basically mass. Mass into gravity is our force, so the total term becomes force. Now we will divide this equation by delta x, delta y and L, and then we will multiply with minus 1, and then we will use differential property. Differential properties. So we will get d by dx 5x plus d by dy of 5yz plus 5zz and z equal to minus 5zz and z equal to 0 upon a minus rho g is equals to 0. Now we will substitute fluxes in this equation. So we will get d by dx of tau xz plus d by di of tau yz plus since velocity at both the surface will be 0, so rho vz term will get cancelled here, and we will eventually get PL minus P naught by L minus rho g is equals to 0. Now we can substitute the Newton's law of viscosity. So we can write this as minus mu dvz by dx plus d by dy of minus mu dvz by dy plus p minus p naught So now we will substitute flux. So the equation will become dou by dou x of tau xz plus dou by dou y of tau yz plus p plus rho vz square at z equal to L minus p plus rho vz square at z equal to 0 divided by L minus rho g is equals to 0. Now xz plus d by dy of, since velocity is not changing in z direction, we can cancel out this term. They will basically be the same value. Then this will become PL plus rho GL minus P0 minus rho into G into 0 divided by L minus rho G is equals to 0. From here we can see that when this L cancels out with this L, this rho G will cancel with this rho G. And now we can substitute Newton's law of viscosity. So tau xz will be minus mu dvz by dx and tau yz will be minus mu dvz by dy. So now we will get minus mu dvz d square vz by dx square minus mu d square vz by dy square plus pl minus p0 by l is equals to 0. So we will put here dou square vz dou x square minus dou square vz dou y square is equals to p minus p by d. It was given to us in the question that Vz is equals to P0 minus PL 4 mu L beta 1 minus the square 1 minus x square whole square 1 minus y whole square. So we will differentiate with respect to x first. So we will get dou vz by dou x is equals to P0 minus PL 4 mu L 1 minus y by b whole square 0 minus 2x by x. We will again differentiate with respect to x to get the dou square vz by dou x square tau. P0 minus PL on 4 mu L beta square 1 minus y by beta whole square minus 2 by beta square. So this gets cancelled. So we get dou square vz by dou x square as P0 minus PL by 4 mu L into minus 2 into 1 minus mu L beta whole square. In same manner, if we differentiate Vz equation with respect to y 2 times, we will get dou square Vz by dou y square P0 minus PL on 4 mu n into minus 2 1 minus x square. Now we will substitute this dou square Vz upon dou x square and dou square Vz upon dou y square in our initial equation. So minus 2 into P0 minus PL on 4 mu n into 1 minus x square b whole square plus is equals to P0 minus PL upon mu n. So from here, this P0 minus PL term will get cancelled, mu L term will get cancelled, and we will get minus 1 by 2 2 minus x square b whole square minus 1 by b whole square. So here we will get x square plus y square minus 2b square is equals to 2b square. This will get cancelled and we will achieve x square plus y square is equals to 0. But this is not possible. Adding square of two numbers can never be 0. So velocity profile is incorrect. So Vz does not satisfy differential equation. I will once again repeat the problem. So this was our square duct, vertical square duct. We took center at this point and the directions were specified like y, z and x. We took Cartesian coordinate system. Then because the flow was downward and also it was incompressible fluid, which means that the density is constant, Vx and Vy were 0 and Vz was non-zero. Vz was a function of x and y and not of z. Then we had pressure variation in z direction due to gravity. Then we took our differential shell and applied shell momentum balance after writing the fluxes. Then we multiplied fluxes with their respective cross-sectional, perpendicular cross-sectional area to get the rates. And then we further solved the equation. And after substituting the Newton's law of viscosity, we got this equation. This can be equation number 1. Now this equation 2 was given to us in the question, and then we differentiated it 2 times, first with respect to x to get this equation number 3, and then we differentiated the same equation number 2, which is this equation given in the question, 2 times with respect to y to get this equation number 4. And then we substituted both 3 and 4 in our original equation 1 to check if the velocity profile gets satisfied, and it came out that x square plus y square was equal to 0, which is practically not possible. Therefore the velocity profile is incorrect and Vz does not satisfy the differential equation. Thank you.
Thank you, Nalin, for coming to my podcast. I'm pretty sure that the questions which we solved will definitely enhance the knowledge of our audience.
Thanks, Rupesh, for inviting me to your podcast. It was really nice to be here, and I'm also sure that the audience which watches this video, uh, they will find this helpful, and their knowledge of transport phenomena increases. Thank you.
Thank you.